Hello everyone, thank you for having me here. My name is Kamesh Vishwakarma and I am presenting my master's thesis entitled Deterministic Cinematic Animation via Knowledge Graph Guided Asset Orchestration, completed at Liverpool John Moores University under the supervision of Deepak Chakraborty. The central question driving this work is, can we move from the black box video generation toward a controllable, reproducible cinematic pipeline? That is the thread connecting everything you will see today. AI video generation has advanced at a remarkable pace. Systems now produce visually convincing clips from short text prompts. If you have used tools like Runway or Sora, you have seen this firsthand. The output quality is impressive and the diversity is striking. But here is the tension. In production environments, film, animation, VFX, visual quality alone does not get the job done. Teams need four things that current diffusion systems struggle to provide. Determinism, so repeated runs are stable. Editability, so one small change does not require rebuilding everything from scratch. Reproducibility, so the same input reliably produces the same output. And asset reuse, so characters, props, environments, and environmental elements persist across shots and projects. End-to-end diffusion pipelines are visually strong but operationally fragile for iterative production workflows. That is the problem this thesis addresses. Here on the left, you will see the strengths of diffusion-based pipelines: photorealism, visual diversity, and prompt-driven generation. These are the real achievements, and the pace of improvement is accelerating very high. On the right side, the production gap you will find for diffusion-based pipelines. You see, determinism, editability, reproducibility, and FFU. These are not nice to have, they are operational requirements. A director who cannot guarantee that a character looks the same across 50 shots does not have a usable production tool. Now, since we understood that there's a gap, this gap gives us or helps us define three research questions. Research question one asks, can a manifest first deterministic orchestration maintain temporal coherence across complex cinematic sequences? In plain language, we can say if I give the system a structured plan, does it produce stable, flicker-free output frame after frame? Research question two asks, can knowledge graph retrieval improve asset reuse rates and enable structured incremental editing? That is, does remembering what assets are available actually help the system work smarter across multiple runs? Research question 3 asks, can a stage architecture, that is, one that separates planning from the rendering, improve practical compute efficiency and workflow performance? The objective was not to merely propose this idea, but to build a working artifact and evaluate it with measurable evidence. Now, this moves us to do a literature survey. So when I do the literature review, I examined the leading diffusion and controllable video system, including Sora and Runway. Alongside research on controllability approaches such as ControlNet, DragNova, motion guided generation, the strength of these systems are clear: photorealism, diversity, and strong prompt-driven generation. But three persistent gaps emerged across the literature. First, non-deterministic outputs hinder repeatability. Running the same prompt twice gives you two different clips. Second, weak asset persistence obstructs use. There is no structured memory of what was generated before. Third, limited support for incremental editing means that changing one element often requires full regeneration. The gap is not in the creativity potential, it is in workflow structure and operational control. The gap is what this thesis targets. Now, let me properly specify the research gap, right? And what our thesis would claim. No existing system provides us a complete, evaluated, knowledge graph guided deterministic cinematic assembly pipeline at this scope. Individual components do exist, like graph databases, game engines, LLM planners, but they have not been integrated and evaluated as a unified production pipeline. My thesis claim is deliberately scoped. I do not claim universal superiority over diffusion systems. Instead, I claim three properties, each supported by evidence that I will present shortly. First, strong temporal stability and reproducibility through manifest first deterministic assembly. Second, practical asset reuse gains through warm state knowledge graph retrieval. Third, transparent workflow metrics supporting production level evaluation. These three claims are the backbone of the evaluation that follows. To do that, the methodology that we follows, or we can say methodologically, this thesis follows design science research because the core contribution is an engineered artifact plus evaluation, not a purely theoretical contribution. The cycle is standard. Problem, problem identification, define objectives, develop the artifact, evaluate it, find the deviations, again make the changes like develop the artifact, re-evaluate it, and once we are done with this cycle, this loop, we go to communicate the outcomes and limitations. The artifact is synonym render, or we can say cinematic animation render pipeline, which serves as the primary production path. I also built instrumented evaluation runs to collect structured telemetry for repeatable metric logging. This dual path approach kept implementation realism. The system actually produces cinematic video while still collecting systematic evidence. Now, if we go a bit deep, right, we can see how our end-to-end architecture for this entire cinematic animation under pipeline looks like. Right. Uh, this slide shows the full pipeline. On the left part, you will see a text prompt enters the system. It passes through knowledge graph retrieval, page retrieval, where Neo4j matches the intent against indexed assets using semantic embeddings. The LM generator agent then produces structured directives, which are parsed and validated into a manifest file. The name of this manifest file is more often than not is scene manifest.json. It will be overwritten once the new manifest generated. That manifest is the deterministic contract. It is a single source of truth for everything that follows. On the right side, you will see that the deterministic stage, in this deterministic stage, Unity receives the manifest, assembles the scene from prefabs and animations that it got from the new project graph database, controls cameras through Cinemachine, which poses which path the Cinemachine path code was written in scene manifest that we just recently generated in the previous stochastic stage, right? And then it renders to frame sequence and MP4. The critical design decision is the separation between these two halves, planning and rendering. Planning and retrieval are allowed to be stochastic. The LM can generate different creative choices each time, but once the manifest is written, Everything from that point onward is fully deterministic. Same manifest, same output, each and every time. The separation is how this pipeline achieves controllability and reproducibility together. At the implementation level, the Python layer handles prompt processing, knowledge graph retrieval, LLM interactions, manifest parsing, and validation. The Unity runtime scripts manage scene instantiation, animation control, camera direction, and final export of frames and MP4 file. Neo4j, which is the graph database, stores persistent semantic memory for assets in the embedding model, which generates 768 dimensional embeddings. The runtime stack is Unity 6.2 for our current cinematic render pipeline version. But let's say it will work for any of Unity 6.x version, right? With Cinema Machine for camera control, timeline for sequencing, and recorder for export. An important practical detail, all of this runs on consumer hardware and NVIDIA RTX 3060 with 12 gigabytes of virtual RAM with 96 gigabytes of system RAM and an Intel i7 12700K processor. This is not a hyperscale cloud deployment. It runs on a single workstation, which I believe is significant for demonstrating practical accessibility. The evaluation for the frames and MP4 video output that we have generated has two complementary parts. Frame level metrics measure the quality of the rendered video output, like interframe SSIM for temporal coherence, background SSIM for static element stability, and a luminance delta flicker metric adapted from WCS framework, and cross-run PSNR and SSIM, where aligned second runs are available. Workflow metrics measure the orchestration behavior, manifest validity rate, edit assembly success rate, asset use rate, run reproducibility factor, manifest build latency, and edit response time. A key distinction is that frame level metrics are always available from any exported video. Workflow metrics require instrumented runs with structured status logs. This scoping is important for understanding which results are reportable and which remain conditional. Now, temporal, uh, this, if you see this chart shows the running mean for all 239 frames, which were generated for full HD resolution, um, of the primary scenario where the in here the y-axis is structural similarity and which says it is higher is better, right? So the interframe SIM mean value is 0.9684, right? Then strong scene consistency is 0.9848 and low flicker value is 0.8817. The starting value is 0.9794 during the static warm-up phase. As motion begins, there is a predictable dip at 0.9606 at peak motion around frame 90, which is expected. Moving object naturally change frame structure. The curve then stabilizes and begins recovering as the sequence progresses, reaching 0.984 by the final frame. The background SSIM of 0.9848 is particularly strong, indicating that the static scene elements remain rock stable throughout, where lower local SSIM value appear. They align precisely with expected camera transitions, not random instability. For cross-run comparison, I aligned frames from two independent runs of the same manifest and measured pixel level agreement. For cross-run PSNR, the value was 50.46 dB, and SSI cross-run SSIM is 0.9011. For PSNR, above 50 decibels indicates near lossless reproduction. For reference, PSNR above 30 dB is generally considered acceptable for video. So 50 dB is well beyond that threshold. The residual difference comes from expected factors such as video encoding and minor runtime rendering variations, not from systemic instability. This directly answers research question 1. Manifest first assembly yields run stable reproduction under practical conditions. Now, now the workflow matrix, and I want to be transparent about what worked and what did not. Starting with the strengths, manifest validity rate is 1.00. All four generated manifests were structurally valid and schema compliant. Run reproducibility factor is 1.00, perfect deterministic reproduction across repeated executions, and the strongest finding asset reuse rate. In cold runs, where the knowledge graph had no prior history, the reuse rate was 0 out of 9 assets. After warm-up, it jumped to 9 out of 9, 100%. Every required asset resolved directly from the graph without fallback generation. This is the most direct evidence for research question 2. Now the gap. Edit assembly success rate is 0.50. 2 out of 4 assembly attempts succeeded. The failures came from specific integration issues during the evaluation window, asset loading mismatches, and animation binding errors that did not trigger graceful fallback. Manifest field latency averaged approximately 180 seconds, and edit response time could not be measured in the current test runs due to the export stage constraints. These are honest limitations, and I will address what I learned from them shortly. Uh, there's another extended valuation for with another scene, 601 frame scenario. To strengthen the evidence base, I ran an extended evaluation using a two-night concentration sequence across 601 chronological frames. This tested temporal stability at a larger scale and a more complex scene interaction. Interframe SSIM mean was 0.979, background SSIM was 0.987, then flicker index was 0.9779. Mean motion difference was 0.0000462. These results are consistent with the primary scenario and in several metrics stronger. The flicker index of 0.9779 compared to 0.8817 in the shortened run suggests that longer sequence with more stable camera work actually reduce perceptual flicker. Since this was a single run media export, cross-run metrics were not computed here, but the frame level evidence reinforces the temporal stability findings. Let me now interpret the results with appropriate nuances. This pipeline is strongest where deterministic controllability, reproducibility, and structured asset use matter most. If a director needs the same character to appear identically across 50 shots, a diffusion pipeline would require consistent reference images and still produce variation. This pipeline guarantees it because the same prefab is loaded from the manifest every time. Diffusion pipelines remain stronger for unconstrained open domain photorealistic diversity. If the goal is a single one of creative clip with maximum visual novelty, diffusion is the better tool. But if the goal is a structured, editable, reproducible cinematic sequence, the evidence supports a manifest first approach. The practical conclusion. is informed architectural choice based on production objectives, not absolute replacement of one paradigm by another. I want to explicitly acknowledge the limitations of this work because they define the boundary of my claims. First, the edit assembly success rate of 50% indicates that orchestration robustness needs significant improvement. Second, edit response time measurement was not captured in the current evaluation, limiting workflow performance insights. The third, the system depends on curated knowledge graph quality, incomplete assets libraries uh, that will constrain retrieval effectiveness. Fourth, the only implemented backend is Unity, which limits centralizability. Fifth, hardware constraint on the current workstation limits scaling to very large scenes. And finally, not all frontier baselines were treated locally under parental controls, which constrains the directness of comparison. These limitations are not afterthoughts, they are engineering that I tracked throughout the project, and they directly inform the future work. The thesis contribution has four concrete parts. First, the cine anim render pipeline artifact itself, or the cinematic animation render pipeline, the artifact itself. The first complete evaluated knowledge graph guided deterministic cinematic assembly pipeline at this scope. Second, a dual path execution model that separates the production runtime from instrumented evaluation, enabling both creative output and systematic measurement. Third, an applied metric framework, combining frame level quality evidence with workflow level production evidence. Fourth, empirical demonstration that warm state knowledge graph retrieval achieves 100% asset use, up from zero in cold state. All four contributions are grounded in working code and measured evidence, not theoretical proposals. Um, Future work follows directly from the observed bottlenecks in priority order. First and immediately and importantly, we need to improve the assembly success rate through enhanced error handling, recovery mechanisms, and robust manifest validation to close the EASR gap. Second, integration real-time edit response tracking to enable edit response time. Measurement of edit response time and support iterative creative workflows. Third, extend knowledge graph coverage and automate asset enrichment to reduce manual curation overhead. Fourth, explore integration with additional rendering backends and cloud-based workflows to test scalability. Fifth, conduct larger scale human evaluation studies for perceptual quality and usability. The first item is the highest priority because the ESR gap is the most impactful and important limitation on practical deployment. Now, to conclude, this thesis demonstrates that deterministic knowledge graph guided cinematic assembly is feasible, measurable, and practically deployable in consumer grade hardware for structured scenarios. The strongest evidence, temporally stability, temporal stability, sorry, temporal stability with SSIM values consistently above 0.96 across hundreds of frames, reproducibility with cross-run PSNR exceeding 50 decibels, and a knowledge graph that goes from 0 to 100% as it goes after warm-up. And that brings me back to where I started. The question was whether we could move from black box generation to structured, reproducible assembly. The evidence says yes. Limitations are documented, and the next steps are clear. Thank you for your attention. Let's to conclude the thesis.